So pressure is equal to force over area. So then how do we calculate pressure? So in a simple example would just be like, a box on the ground. And then, so we can ask the question, for example, what is the pressure of the box on the floor? Then, assuming it's like 3D, right? And then the floor is also 3D. You can say, all right, so what is the force that the box exerts on the floor? And this is going to be equal to the weight, right, which is mg. And then the pressure by the box on the floor is then just equal to mg over whatever this area is, right? So mg over a. Cool. So now that we have this, we want to talk about more how pressure is applied to a fluid instead of to a solid, right? So let's just say that you had some container of water, right? Yeah, and then it's three-dimensional. So, okay, I did not draw it in the best way. Let me just do that again. Oh yeah, units, right? So what are the units? What is the unit of pressure? What is the pressure unit from looking at like F over A? Newton over meter squared. Good, because the force is the Newton and area is meters squared, right? And this is also called a Pascal, right? Or a kilopascal. Is it a kilopascal or I think it's just a normal Pascal.
Yes, 1 Pascal is 1 Newton per square meter.
Yeah, so this is just 1 Pascal, Newton per square meter. Okay. So then how do we look at it in terms of fluids? So let's just say we have like a container of some sort, right? And then fluid is filled up to some level. Just say it's here. Right, so first of all, there's something that exerts a pressure, like if something is on Earth, right? There's something that exerts a pressure on everything on the surface of the Earth without there having to be like water or a solid or anything. No, gravity does not exert a pressure because a pressure is like something weighing downwards. Gravity is a pull, right? Air, good. So then what is like the pressure from air called? Yeah, it's air pressure, atmospheric pressure, right? So air pressure or atmospheric pressure so always exists.
Wherever there's an atmosphere.
Yeah, assuming there's an atmosphere, but uh, okay, don't vacuums exist on Earth? Well, yeah, we're assuming it's not in a vacuum. So atmospheric pressure always exists, assuming the atmosphere actually exists, right? And then, like near the surface of the Earth, we say it's like roughly the same. It's called like 1 atm. So do we actually know the conversion between atm and pascals? I don't.
101.3
1.3.
kilopascals.
Yeah, so equals to 101.3 kilopascals. Right, okay, so you don't have to know this, but it's just here. Okay, so that means at the top of this water here, there's going to be atmospheric pressure, just like at the surface of the water. Right, okay, but then let's just say that you were at some depth beneath the surface of the water, right? Let's just say you were, what? Okay, let's just say you were here, right? And then, and then the slice of water that you were in is like this slice right here. And then the distance between the surface and like the slice of water that you're currently on is h, right? This is the distance. All right. And then let's just call ATM like the pressure at the surface, right? So whatever that may be. This is pressure. Let's call it P naught, pressure at the surface. So what is the pressure that is experienced by an object that is like h deep from the surface? Right. So let's derive that. So first of all, does anyone know already, or like have an explanation? No. All right. HA times G plus P naught. Wait, let me actually write that out. P naught plus HA times G. All right, so what is A? H rho G plus P naught. Yeah, so A is the, so then AH is just gonna be, yeah, you need density, right? So, okay, so this is P, and then the density is rho. Let's not assume, let's not confuse our P's and rho's. Uh,
So
yes, how do you
yeah.
write rho that's different from a P?
So here, let me grab my tablet. It's
All right, I'll just do
charging over
this.
here.
Density is equal to rho, and then we're assuming that it's water, right?
It's
So
better
rho,
to write. Oh yeah, sorry. Go ahead.
so density is rho W is equal to the volume over the mass, right, of the water. So then this doesn't make too much sense because this is a volume unit and this is a force unit, and then that doesn't quite make a pressure unit, right? There has to be like, there has to be a rho here. I don't think this is quite right, actually. No A. Yeah. So this is actually correct. So then P at H. Let's call this like P at H. Pressure at height H below the surface. So yeah, so pH is equal to rho, P0 plus rho GH. So how are we gonna get this formula? Are you capital P for pressure, P lowercase for density, or rho for density? All right, yeah, sure.
Yeah, I just put that.
So how do we get this? I'm gonna redraw this container. This is filled. Actually, I'm not gonna draw the lines. Makes it unclear. Is this small or big P? Yeah, we're gonna say big P is for pressure, and you are somewhere here. Okay, so then first of all, it should be kind of intuitive that pressure is additive, because if something is weighing on you and something else is weighing on you, then you have two things that are weighing on you, right? So yeah, we're gonna add the pressure of the atmosphere and the pressure of the water that is above you, because the water is the other thing that is weighing down on you, right? And then, so what is the, so if I were here, right, and then this is equal to H, then what is the mass of the water? What is the mass of the water that is like weighing down on you?
Just before you answer that, just again remember, pressure is only additive if the force is being applied over the same area.
Yeah.
Like if we're exerting pressure on two different areas, those two will not add, because that's not how fractions work. All right, keep going.
Yeah. So on the dot, or like just on the entire area, on the entire slice that I the entire slice that I, kind of drew out, right? So what is the mass of the water that's on top? If this is A and then that's H, and density is rho. Okay, yeah, so the mass is equal to rho times A times H, right? And then, so because this is the mass, then, and gravity acts on this entire block of water on the surface, right? Then what is, yes, and this is equal to rho v. So in this case, what is the force that is exerted on the slice by the upper block of water from because like of how gravity pulls down that block of water? Because like we can go back to our box, right? Yeah, rho vg, because if the solid box exerts a force of mg on the ground, right? Then this box of water also exerts mg on the slice of water that's beneath it, right? Okay. So therefore, the force of the block on the slice is equal to mg, which is equal to rho ahg, right? Let's not make the substitution v equals h, just like right now. Okay, but then what is our formula for pressure? Yeah, the a cancels out when you divide. But then, yeah, so then pressure is equal to the force over the area, right? So that means the force by the block on the surface is equal to rho times A times H times G, and the bottom is just the same area, right? And then this means we can actually cancel out the A's, and then what we get is just purely from the block on the surface, we have the pressure is equal to rho times G times H. Right, but then because of like this additive thing, we have to add back the pressure from the surface, right? Which is the pressure by everything that is above the water surface of the water onto the block, which transitively acts on the slice that I drew out here, right? So then, therefore, we can say that the pressure at some height below the Earth's surface or the water surface is equal to P naught plus rho GH. All right.
This is called gauge pressure, by the way,
Yeah, and this is called gauge pressure. Okay,
not
so any
gouge.
questions so far? Loggers. Okay. Any questions? Yeah, P naught is, it's not called air pressure, it's called atmospheric pressure. It's the pressure of the atmosphere on everything that is below the atmosphere, which is everything on the surface of the Earth. And pH is total pressure, yeah. Well, but then in some problems, you might have a specification that the thing on the surface is different. Like you might have a layer of oil on top of the layer of water, and then you have to calculate that separately.
Or you start out higher up in the atmosphere where it's thinner.
Yeah, or
Then
you
it's
might
just,
be at some elevation where the atmospheric pressure is less than it is on the ground because the higher up you go, the less air there is, right? Like the air is extremely thin on top of Mount Everest, for example.
linear
Yeah,
combination.
it's a
Well, I mean,
linear combination.
of course it's a linear combination, right? Because what's the pressure at the height? It's like some sort of atmosphere. Right? It's some amount of atmospheres, which is just some constant times one. So yeah, technically, yeah. Okay, so that's gauge pressure. That's one type of pressure. This is like this is the most basic fundamental type. There are other way more complicated types that we probably won't go into with too much depth.
Gauge. What does gauge mean?
What does a
I'm not
gauge
that good
mean?
with words.
Well, okay, so a gauge, like, it measures like it's like a. Have you ever like been in a car? Do you like you see those little things that measure the speed and like the amount of gas and like the little arrows that move? Yeah, those are gauges. So basically, it's like some sort of device that like lets you measure the magnitude, amount, or content of like anything. So I guess it's called gauge pressure. I don't know. It's because it gauges the amount of pressure at the height. Um, yeah, to gauge something means to measure it. So yeah. What other pressures are there? Well, we'll get into it. A
There's
bit.
like a lot of pressure involving solids that are more complex than in liquids, I believe. But that's something for another time. So now we're going to do something called Pascal's principle. Is it called? Yeah, it's called Pascal's principle. All right, we're going to go back to our container. But this time it's a circle because it doesn't actually matter. All right, so first let me ask this fairly basic question. All right, what determines whether or not something floats? So like what things float and yeah, density, right? So how does density affect uh, like why something floats? So like if you've ever done the thing where you drop different objects into a fish tank, yeah, if density is greater, then it doesn't float.
Greater than what?
Hmm?
Greater than what?
Greater than water density. Yeah.
Okay, or the liquid that it's in. Like if it's an oil, greater than the oil density. Yeah, just a bit more specific. Yeah.
Okay, so does anyone have like an idea of why things float or things don't float because of their density? All right, let's go over that. Oh yeah, because if something is more dense, the pressure on the bottom counteracts gravity.
Okay,
Hmm,
well, it does.
not really.
Let's first address Mohammed's thing. If something is more dense, it doesn't necessarily have less area. Like I can take a giant ball that is way like I can take like a giant bowling ball that's way denser than a tiny like ping pong ball, right? Bowling ball is still gonna sink, but the ping pong ball will float. Um,
Let's drop a black hole into the ocean. That's a good idea. Okay,
can't float if there's no ocean.
so what is Pascal's principle? I'm gonna switch colors actually. Well, let's just say you had some object, right, in the middle of a tank of water. And then, there's a lot of objects that kind of, okay. Uh, yeah, and then let's just say like it's floating somewhere in the middle of your tank of water, right? Okay, so now let's do some force analysis of on this object. So what forces are acting on this random object in the middle of the water? Well, firstly, of course, there's going to be gravity, right? There's force due to the gravity. And then, however, we know that since the object is floating, it's not moving downwards or upwards, right? So that means there has to be another force that acts upwards. Yeah, it's called the buoyant force. Good. And we're going to call this force FB, right? So because the object floats, the buoyant force must cancel out the gravitational force.
I'd be careful with equating the buoyant force to the normal force, Arid, because the normal force is just the force that acts perpendicular, that acts perpendicular to the surface.
Yeah,
But
we're
there's
not
no
really
surface
talking
of
about
the fluid.
surfaces here with fluids. Like a surface is only you can only talk about a surface if the thing is solid. So why does buoyant force exist? Well, good question. That's what I'm gonna like build into, right?
Okay, that's a good starting point. Yes, every action has an equal and opposite reaction.
Right. So how do we write this out quantitatively? We want FB equal to FG, right? Um, Actually, I did this wrong. Actually, no, I didn't. So FB, so what is the force of gravity? Yeah, mg, right? Now, actually, I'm not going to assume the object to be, I'm not going to assume the object to be weird shape. I'm actually first going to assume the object to be a cube. Because then, you know, if, and this cube has an infinitesimally small volume and also an infinitesimally small mass, right? Because after I'm done with the cube, I can just say that any other object is a collection of these small cubes, right? So then we're gonna look at a small cube. And the cube has a mass of dm and a volume of dv, right? Which is equal to some d area times dh, right? Okay. So then this means that, oh yeah, also density of rho. Let's just say it's rho of the cube, right? As opposed to rho of the water. Okay, so so then that means this is mg is then equal to rho of the cube times dAdh times g. But now, what causes the buoyant force? Well, the buoyant force should be caused by the difference in pressure at like the two heights at which the cube lies, right? Because the pressure here is a downwards pressure of like some P0 plus rho of the water times G times H. But then at the bottom of the cube, there's going to be some other pressure, right? It's actually going to be a greater pressure. So this is going to be, is it going to be D? We're going to get into that. So this is actually going to be like P naught plus rho of water times G times like some H plus DH, right? And then this is actually going to have like a slightly greater magnitude. And because like there's a smaller pressure on top of the cube than at the bottom of the cube, then like this is going to be what's causing a small upwards force. Like, do you guys all sort of understand where that comes from? It's like, it's kind of like the thing with an airplane, right? Because if the pressure on top is less than the pressure on the bottom, then the plane's wing like floats, right? Like, is there any questions on that?
Yeah, why is it greater? Like, I understand why there'd be a difference, but I don't really see why the pressure. So the pressure on the bottom is greater, right?
Yeah.
And so the buoyant force on the bottom of it is greater than the buoyant force on the top of it.
No, I'm saying like the pressure difference creates a force that goes upwards.
Why would it create a force?
Well, if you think about the plane, right? So what makes a
I don't know
plane?
anything about aerodynamics or whatever it's called.
Okay. Plane. Yeah, so if we'd like to take a look at the cube, right? All right, so what is the pressure that is acting on this top surface?
It's P naught plus P WG times H.
Yeah. Rho zero plus, and then what about the bottom?
It's that bottom equation that you wrote.
Yeah, so this is rho zero plus rho WGH, but then like because you're adding this DH, right? So this is, you're also adding some rho WGDH, right? Why is the direction upwards? Well, because the buoyancy force needs to be upwards to cancel out gravity. Right? And then we're just talking about like how it floats, right? Okay.
Why is there a pressure on the bottom if all the water is on top?
No, I'm saying like there's always going to be a pressure on anything that is at that water level. Yeah, so it is upwards because, okay, because like if you think about the forces that act on the sides, right? Then it should be the same because the pressure from all the water that's here and the pressure from all the water, no, the pressure from all the water that's on the left and on the right of the cube, because like the pressure is the same at like each of these levels, then it cancels out the force that's acting, it cancels out the pressure that's acting on the walls of the cube on the side. But then the only differences there are is on the top and on the bottom. Like the top, the pressure on top is different from the pressure on the bottom.
Oh, so we subtract that top equation from the bottom equation, and you're left with that third term?
Yeah, exactly.
And that's the pressure difference that pushes it up.
Yeah, so then since the bottom is being pushed down like more than the top, right? But this can't happen because we're also assuming like this thing to be incompressible actually. So
the height of the object, what if it's wide? Like, does the width matter? Only the height matters, you're saying?
no, we're assuming the cube to be infinitesimally small.
Okay, good.
I think it's important.
Incompressible is the same as the chem definition, which is the density doesn't change, right? But then, yeah, no, this is also why like a lot of objects get crumpled up at the bottom of the ocean because of like just all the pressure, right? But then there's a contradiction here because the top is experiencing a different magnitude of force than the bottom, right? And that means the object is compressing, but then the object is assumed to be incompressible. Therefore, there has to be a force that counteracts like this small force element here that's acting on the bottom, right? So then that's what creates like a small DFB, which is the buoyant force.
So how do we convert that third term into force? We multiply by area?
No, we're gonna do that later. Right, so yeah, does anyone have any questions? Because I think I might have put it in a confusing way. But like this
Just
buoyant
for anybody,
force
oh, sorry.
exists to counteract the difference in force felt by the top and the bottom, right? And then it just comes from, you know, the object wanting to stay in shape. So then there has to be like another force that's acting to not compress the object. water doesn't change. Isn't the pressure into the cube not away from? The pressure is always like downwards. So down on top.
Well, actually, yeah. Yeah,
Yeah, so then
the
if you
pressure is
just
always.
envision the cube as a point particle, right? Or as 2-point particles that have to stay the same distance apart at all times from incompressibility, right? The bottom is experiencing some force F plus dF, and the top is experiencing a force F. Yeah, and the top is experiencing some force F, right? But then since, the bottom cannot be compressed, then that means there has to be like a force on the bottom here, dF, that is counteracting it, right? So then like both surfaces will be experiencing the same force F downwards, and then the object will stay in like whatever form it is. That means a
Yeah,
flat object will always sink. No. Wait, why is that?
well, water lilies are flat. Do they sink?
Well, nothing
Like,
is
they're
They're not
really
plates.
truly
flat.
flat,
Yeah,
right? Because
nothing's
there's
like really
always some.
flat.
Sorry?
But like assuming something was flat, it would always sink.
I don't know, a piece of cardboard.
That's
That
not
floats.
flat. Like
Oh, you're talking about a
nothing can
two-dimensional
act
object.
nothing can
Do you
actually
mean like
be flat.
like
But,
a truly
like-
flat object?
Yeah, assuming something truly was flat, it would always sink.
Yeah. But
Okay.
no, but like you're envisioning a two-dimensional object in a three-dimensional world, and that's weird.
Also just impossible.
Yeah, because like the tub of water is three-dimensional, and then you're putting a two-dimensional object in it. That's a really weird and impractical thing to think about. But I guess so, because there wouldn't be a second surface. But like in assuming that another object is made up of like a series of these little cubes, we're assuming that there is at least a little bit of height, like dH to it, even if it's just made up of like one layer of these cubes, right?
You can still create like by truly flat, like I guess in our world, the flattest you can get is if it's one atom thick. So let's say our surfaces, our object is one atom thick. If the force exerted down is not enough to break the surface tension of the water, it will float on the surface of the water. If it is strong enough to break that surface tension, it will sink. So like, consider like, for example, like water spiders or water crawlers or whatever they're called, like, their feet, like those flat parts are not strong enough to break the surface tension, and so they won't sink. At that point, it's a lot of other weird stuff. Or the lizards that can run on water, yes, they also press flatly. But that's like a completely different topic for a completely different discussion.
All right.
Not even sure we can get to it today.
My Zoom crashed. All right. Well, you're back now. Yeah, so if anyone has any questions, please ask, because this is like quite a confusing thing to understand at first, like how the pressure difference creates a force that makes something go upwards from force balancing.
Oh, it's also important to like worth mentioning that like to those of you who didn't take chem, I'm not sure which of you took chem or didn't take chem, but I'll just quickly summarize what incompressible means. So like if you compress an object, you're compressing some sort of mass into a smaller volume, which naturally increases the density, right? Because same mass, smaller volume, bigger fraction. But with a fluid, the idea is, or with an incompressible fluid, if you compress that mass, the volume, the volume like will also compress in the same way. So you can't ever fit a smaller mass of that liquid into the same mass of that liquid into a smaller volume. That's not necessarily the case for some things. Like there are things that, there is no such thing as like a truly incompressible fluid, but Like, yeah, that's what we mean. So for those of you who didn't take chem, that's what incompressible means, just to clear it up. But yes, so Arib, to answer like the previous question about like the third law pair, this is kind of a third law pair. Also, sorry, Alvin, I'll just take like 30 seconds. In terms of like practical things, where does that force come from? That force comes from, water molecules bouncing against and hitting the surface of the object. That's also why Alvin made it a cube, to better illustrate that. So like little molecules hitting the surface generate that overall force. Okay, why would it sink?
Okay, we'll get into that later because we haven't actually used FG, right? We've only been dealing with FB and like what that is, right? Right, so this is also why like a plane has wings that can stay in the air, right? Because there's a pressure difference at the top of the wing and at the bottom of the wing, right? So there's P small and P big, right? And then this would result in a force going downwards, but then this is also going to result in a force going downwards, but a smaller force, right? And therefore, at the bottom, you're going to have like air molecules hitting it upwards so that the force is balanced, right? And then that's why the wing of the plane can actually stay aloft. Okay, any questions on this? All right, so let's continue with this, right? So then, we did it for a cube, right? But then for a general object, it is made up of these things, right? It is made up of little cubes. And therefore it works for a general object, all right? Does this apply to liquids? Like you mean a liquid in another liquid? Well, a liquid in another liquid, it would either sink or float. So yeah, it does actually. But then it just doesn't change like, well, it will still sink or float based on its density, right? But then I don't think we use any property liquid doesn't have. Yeah, it does work for liquids. So liquids are incompressible or mostly incompressible enough, right? And then there's some mass, and then we can say like this is some particle of water, a cubical particle of water. And yeah, it works for liquids as well. Okay. Now we're gonna do the Archimedes principle, right? Which is the last thing, but extended. So we're actually going to continue this, right? So we know that FB has to be equal to FG for it to float somewhere in the water. Right, so Archimedes invented that laser weapon. I don't think there were lasers back then. Laser mirror, maybe. This is equal to mg, which is equal to rho dA dH times g, right? But then what is the buoyancy force? Well, the buoyancy force exists because of the pressure difference from the bottom and the top of the object, right? So then we can say that because the pressure is equal to the force over the area, then we can also say that the force exerted by the pressure at like two different height levels, is equal to the pressure times the area, right? So this is actually going to be equal to, well, what did we have before? It's going to be equal to the difference between the pressure on the bottom and the pressure at the top, right? So the force is caused by the force by pressure on the bottom minus the force by pressure at the top, right? And then we can use PA equals F to get that this is equal to, the area is going to be the same, right? But then you have the pressure at the bottom minus the pressure at the top, okay? And this is going to be like dA because we're still working with the cube. So if we set these equal to each other, PC dA dHg is equal to dA times P flat minus P of the top. We can cancel out the dAs, right? And then we get rho C times G times dH is equal to the difference in pressure. So, but then what is this difference in pressure? No, like based on what we had over here, right? It's rho of water times G times dH, right? So right, and I'm actually gonna okay, yeah. So this is so FB is equal to and this is equal to volume, right? So this is equal to rho times V times G. But then, you know, the force required to keep something at the top is equal to like rho of water times G times dH, right? Times dA actually. So then in order for something to float, you have the buoyancy force is equal to, is greater than or equal to the thing of the water, right? So rho of C times rho of C times V times G is equal to rho of water times G times the volume of the water times G, right? So then, or actually this can be like greater than or equal to, right? Because if the buoyancy force is greater than the force of gravity, then it's just gonna like float on top of the water, right? And then there's gonna be less of the actual object on top, right? So then that means the object floats if the density of the cube is less than or equal to the density of the water. Oh, I condense the dA dH into V. All right, but where did my inequality mess up? Andrew, I need a little bit of help here.
Yeah, I'm looking through it right now. Okay, so you got PC. Okay, so you got that implies that. Uh, yeah, I think it should be PCDH instead of PCDV. Or sorry, instead of PCVG.
Wait, on which line?
So if we go to you see right there, like in the very final line where you're describing floating,
Yep.
it should be PCDH is greater than or equal to PWVG.
PCVH.
PCDH. Because you see how you divided. So if we go from the very previous line, we have PCGDH equals rho CGDH
Oh yeah,
equals
sure.
rho
Go.
WGDH. Yeah. So you divide by G, you get rho C. Yeah, there you go. And now your inequality should work. Lewis, yeah, sure. What do you want to annotate? D. Yes, DA. That cancels too.
Yeah, and
Perfect.
then with the cancellations, you get, but you have there's a problem with the derivation. It's like trying to debug.
Okay, well, at this point, you see how there's DA on both sides? You cancel DA, there's no V anymore. So it becomes rho WGDH equals rho CDH. Well, it's less than. Yeah, exactly.
Right. All right. Okay.
Hence your inequality.
Wait, but does that follow though?
What does that follow? Okay, like, so you see DA rho C GDH, right? That's your P bottom minus P top.
Mm-hmm.
And that's rho WGV. So V cancels from both sides, DADH cancels from both sides, and G cancels from both sides. So you got rho C equals, is less than or equal to rho W in order for this inequality to hold. Not inequality, in order for the equality to hold. So you can basically cut out and you go immediately to the rho C, rho W thing.
Yeah, okay. Yeah, okay.
Middleman.
So
And this is the case for if it floats at a specific location. That's why it's less than or equal to. So you're saying, if it doesn't sink to the bottom, it's less than or equal to. If it's less, then it'll stay at the top. So if you plop it somewhere, it'll float up to the top. If it's equal to, it'll just stay in one place. If it's greater than, then it'll sink. That's where the inequality comes from.
well, actually, I can. I don't actually need all of this. Because yeah.
We're having some intellectual difficulties. Let's. I'm not doing well with puns this year. Okay, so let's start again. So everybody who's been taking notes, scratch them. We're going to start from the top again.
So FB is equal to the F bottom minus the minus F top, right? So then this is then equal to dA of P bot minus P top, right? So then, yeah, I forgot I wrote this down. So if we looked at rho of water times G times DH, like this is the difference in forces, right? So this is equal to rho of the water. I don't know why I got stuck on this. Sorry, guys. Rho W times G times DH, right? This is from what we had before. But if you combine the dA times dH elements, like this becomes the volume of the actual object, right? Because this is your dA and this is your dH. And like if you multiply area by height, you get volume, right? So this is actually just equal to rho W G times dV. And this is actually the result that I wanted. Yeah. So rho W G dV, right? And then notice that this actually does not depend on the density of the object itself, but rather it only depends on the volume, right? Because rho W is constant for whatever fluid you're in, and then G is also just constant, depending on the planet you're in, I guess. Yeah. But then volume is the only thing that can change, because if you just sum up all the cubes, right, then that means F buoyant on an object is equal to rho WG, but then when you sum up all the dVs, yeah, I read that's correct. But if you just sum
That's
up
it. That's its definition.
then you just get rho WGV, right? And like this is the thing that I wanted, but I wasn't getting for some reason. And I realized I wasn't just using like this thing I had from before. Yeah, so this is important. But does anyone have any questions on this? You put an extra dA where?
Well, when we were doing it before.
Before?
Yeah, like when during the initial calculations. Guys, this is why dimensional analysis is important, because rho is mass over volume, right? So mass over volume times volume, we're left with then G, which is in terms of newtons, right? So we wanted our force to be in terms of newtons. So mass time density times volume times force gives us newtons, and what we had before did not give us newtons. So good insanity check just for any physics problem.
Some of the tougher, I
Some of
wouldn't say
the
the tougher problems. I'd say the easier problems can be just solved with pure dimensional analysis. But we're going to be going over dimensional analysis in problem solving next week.
So unfortunately, yeah, next week. So unfortunately, the F equals MA has made the exam tougher by putting all of the answer choices in the right unit. So you can no longer cheese it by saying, oh, this is in the wrong unit, so let's cut it out. Of course, there is going to be that rare exception where there are problems on the F equals MA where one of the answer choices is in the wrong unit, so you can immediately cross it out. But it kind of just, they have anti-cheesing methods where they basically put it in the correct unit for you. But yeah, this is just a personal check where you can check if your answer is in the wrong unit, then you did something wrong.
Okay. Yeah, so this is the inequality that I ultimately wanted, right? So then now that we have the buoyant force is equal to density of water times G times volume, and the gravitational force, oh, this might have been what confused me because I wrote FB is, yeah, this is FG. Let me just add that in here, right? So if we want the buoyant force to be greater than or equal to the gravitational force, then we have PWGV is greater than or equal to PCGV, right? And then we can cancel out the GVs. So then this just leads to the density of water is greater than or equal to the density of the cube in order for it to flow. All right, so any questions? why does hot air rise? Because hot air expands a gas, and it is less dense. No, well, air is actually a fluid, believe it or not. You might think, the only fluids are like water, right? But then gases are actually also considered fluids. So, the density of hot gas is less than the density of cooler gas. So hot gas rises upwards by the same principle. Yeah, because oxygen actually also exerts a buoyant force. But like no person is floating around because everyone is dense. But like also hot air balloons work this way. They heat up the air, right? So then it creates a buoyant force so that the hot air balloon can stay at some altitude.
This is the general, oh, sorry.
Yeah, go ahead.
This is the general rule of thumb where gases are typically less dense than their liquid form, which is less dense than their solid form. Typically, because when you press together, it makes intuitive sense. When you press something together more and more, it gets denser and denser. The only, like one of the few exceptions, like a unique exception. Does anybody want to guess what the unique exception is? Water, yes, because ice is less dense than liquid water. Water expands when it freezes, and ice cubes float. But in terms of basically anything else, for any other fluid, typically its gaseous form is the least dense, liquid is denser, solid is the densest.
Okay, so seeing that it's like 5:34, we'll give you guys a 10-minute break. All right, so we will be back at 5:45.
5:45.
I cannot add 10 at this time.
I am especially dense, so much so that I sink in solid concrete.
All right, but like if you have any questions, ask away. We'll still be here.
Why is ice less dense though?
It has to do with like the intermolecular forces, crystal formations, yeah.
Yeah.
Like the chemical bonds, they like get longer. Or something.
And it's just because like because with ice, it uniquely puts itself into like a very specific regular type of lattice, which is, yeah, I guess.
Wait, do you have him for AP Chem Canal? Cool. I had him for AP Chem last year. Good teacher.
I had Kivy. Kivy's dope. I didn't have him for AP Chem because we weren't huge nerds who had to take AP Chem sophomore year. Okay. By the way, does anybody know the story of why it's called Archimedes Principle? How he discovered it? No, nobody knows the story of the gold crown.
Bash a bunch of math, and it turned out
he was not gold in a bathtub. Yes. So yes. So basically, the king. I think yes, a king asked Archimedes. He had a gold crown, and he wanted to find out if that crown was really pure gold. Now, obviously, you don't want to damage it and turn it into a gold bar and check. So you kind of had to find out if it were gold, if it were pure gold without really messing with it. It's weird. How do you do that? So one day, Archimedes was getting into a bathtub. Obviously, this is probably apocryphal. It probably didn't actually happen this way, but he got into a bathtub and a lot of water spilled out. And suddenly, and when he was getting out of the bathtub, he also noticed that the water level lowered. And it is at that moment that he shouted "Eureka!" and realized that the water displaced is equal to the volume of the object of the volume placed into the object. They did have bathtubs in ancient Greece, believe it or not. And so he ran through the streets, supposedly naked. No, Romans had bathhouses. It was a bit different.
Yeah, they had like heated water. It was advanced. So
Archimedes reportedly raced through the streets naked to the king's quart and said, I know how to do this. Let's lower them both in water. Because the denser one will also just displace more water because they're the same size. But, you know, if they're the same size, same volume, but one of them has more mass, it'll displace more. So they lowered them and noticed that it was not, I forget, was it pure gold or was it not? I forget the end of the story, but the point is he figured out how to calculate it. That's what's more important. So yes, that is the story of Archimedes and the gold crown. Okay, see everybody back at 5:45.
All right, it is 5:45, so welcome back. Can I get a hands up from everyone?
Or if you're feeling extra brave, turn on your camera.
Yes.
No takers? All right.
It was like this in all your classes when you're in like the breakout room and everyone's just cameras off, mics off. Sounds incredibly boring.
Like this in physics. I mean, I'm a senior. I literally couldn't care less, and I know everybody. I keep my camera on. I don't know about you guys.
Think about
Oh, you guys are just
Wang's Zoom class.
you guys are just too lazy to turn them off. Nice. Wang's Zoom. You guys turn off your cameras now. You have bad. What else? Well, what other bad? Did you have Garber?
You know, Jerry, he has Garber.
Arib has. Oh yeah. Again, don't tell Garber that I told you this, Arib. But she actually no. Wait, no. You guys were recording. Never mind. Let's carry on.
Okay. So we derive. Stop it. All right, chill. Everyone, chill out. So we derived this thing about density, right? But then, like, this is actually the more important takeaway, because this actually tells you like what the buoyancy force is, right? Or in words, we can actually phrase it like this. The buoyant force is equal to the mass of the displaced water. Right, because think about it like this, right? So we know that FB is equal to rho water times GV from the thing we derived here, right? But then what happens when you combine rho of water with V? Oh yeah, I know I said G. So what is rho water times V? Yeah, it's equal to mass, right? So M water times G, right? So this looks like the force of gravity equation, but then, you know, this is just saying exactly what I have like in words up here, right? And this is a really helpful way to think about it. So like whatever the weight of the displaced water is, it provides the same force, but upwards, okay? Questions? All right. So with that, I want to give a little practice problem. Okay. Why is this important? Because a lot of problems involve floating things. This is just like a fairly simple problem. Let's just say a cube has a density of rho cube is equal to 0.6 times rho of water, right? So what portion of the cube stays above the water? Right? And it's important to keep in mind, like the mass of the displaced water is not equal to the volume of the whole box times the mass of the density of water, right? Because the displaced water is only like this bottom part of the box that's in the water, right? So yeah, that's important to keep in mind. All right, I got an answer. I didn't actually do the problem yet. Let's see if I can successfully do it in my head.
Luis, you got your hand up? What's up?
Oh, he said, he told me an answer. Yeah, I believe that's correct. All right, I'll take a couple more answers. Ooh, which one is it? The second answer, Reeb? All right, yeah. These all look good so far. Any other takers? All right, I wanna have like one more answer submission before I talk about the solution. Yeah, it looks good. Okay, so who wants to explain? Hand raise or something. All right, Reeb, go ahead.
Okay, so I didn't really do much calculation actually. I just thought about it like if that coefficient right there were 0 and the object were sort of weightless, it would float on top of the water sorry, if it were
Okay, so like
if it were
if rho c is less, then it floats more.
yeah. And the more rho c is, the less it floats, the more is underwater. So I assume that coefficient was directly responsible for that. So like 60% of it would be below the water if it's 0.6, and the part above the water would just be 100% minus that, which is 40%.
Okay. That's not exactly the most rigorous way. You made a lot of assumptions along the way, but I guess that kind of works. I don't know, intuition is good. Intuition is always good, but it's not everything. All right, Jeremy, you might want to check that. Mohammed, do you have, how'd you do it?
So basically, it's just the buoyant force equals mg. So I just said PCGV equals PWG and then V2. And then, so you know PW is
Wait,
5/3
hold on, 1 sec. This isn't a P, it's a row.
rho, sorry, yes. Rho C GV equals rho C GV2. And then rho of W equals 5/3 of rho of PC.
Wait, row of W? Oh yeah, row of
Rho
W.
of W is 5/3 rho C.
Uh-huh.
And so you can just plug that in, and then you find out that V equals 5/3 V2. And you know V2 is thus 3/5 of whatever V is, and that's what's underwater. So you just subtract from 1.
Okay. Yeah, so this is like I guess the standard way of doing it. Good job. So I guess I skipped a step here. Well, actually, we can just say that like this is what directly follows from the problem statement, right? It's the same thing, but I'm just rewriting it in a slightly different way. Right. So then if I didn't skip steps, I would have, if I plug this in. Okay, so first of all, this is buoyant force and this is gravity, right? And then
What
these,
is V2 and V1, or just normal V?
okay, so rho C, GV.
Is V2 the displaced water?
Huh?
Is V2 the displaced water?
Yeah. So like what Mohammed used here was that the mass is equal to the density times the volume, right? So this is rho C times V. And then this is where like, this is why it's mg, right? But then rho W, which is the density of the water, times V2 is the displaced water. So I'm actually going to call this a different name, and I'm going to call it like V in, right? So then this is the volume of the water that's displaced, or in other words, the volume of the box that's inside. All right, okay. So now that I have this as well, I can plug that in. So I get 3/5 rho W times G times V is equal to rho W times G times V in. Now I can get rid of this. So we know that, now we know that 3/5 of the volume of the box is equal to the volume that's inside, right? So 3/5 V box is V in. So yeah, that's like, that pretty much solves the problem, because now we just know like what portion of the cube stays above the water, right? So then that means 2/5 of the volume of the box is the portion that's out. And you know, this is what we wanted. So we get the answer that is 2/5. All right, any questions? Or 0.4? Questions? No, all right. I guess we can move on to our next mini topic, which is Bernoulli's principle. Bernoulli's principles. Well, let's first consider like the way in which water comes out of the faucet. Now we're going to be discussing something called like laminar flow. So when water comes out of the faucet, like what shape does it take on? Like, is it just like a straight line downwards, or no, it's actually not just a straight cylinder. It's actually more like more like this, right? It actually gets a little bit skinnier as it goes down. Anyone ever observed that? No? Well, after, yeah, so after we get off, I don't know, you can take a look at your faucet. There we go. Ooh, it makes this weird shape. So I guess since no one actually knows about this, like, anyone want to take a guess? Yeah, clear and smooth water flow. I have a DM from someone. Who's that? Okay, never mind. Okay, so anyone want to take a guess as to why the water gets skinnier? Oh, by the way, you can't have like too much water flow because of water's thing that starts with the C. What would that be? Like the capillary action cohesiveness? It's not exactly. That's not exactly the reason. Might play into it. But let's consider. Yeah, that's not exact. That's like you're citing chem things. That's not the reason why. Okay, so we can define the flow rate R as the volume of water per second that goes through like this little cross section, right? So this is equal to the flow rate equals to volume per second equals to meters cubed over seconds. But then what does this, how else can you arrange like this combination of units? Yeah, V times A. It's actually pretty interesting. Is equal to the velocity times area. Right. Okay. So we can take two different cross sections. Let's call this cross section 1 with flow rate 1, and we can call this cross section 2 with flow rate 2. Right. Okay. So this is something called the continuity equation. Which claims that anywhere along like this little pillar of water, the flow rates are the same. So R1 is actually equal to R2, therefore like V1A1 is equal to V2A2. Right, but then the basis of this, yeah, exactly. This just comes from conservation of mass. Because at any point in time, like the actual amount of water like is the same, right? Like because of how gravity works, because of gravity and how everything accelerates uniformly due to gravity, and like at any point in time, you know, the flow rate has to like be the same, right?
Volume flow rate, by the way, is typically denoted Q, but I think we'll leave it at R for now.
Yeah, okay. Okay, so Lewis said something in chat. Yeah, this is why, this is like a good explanation of why. So if the flow rate were any different, then that implies that water has like disappeared, right? And then we can't have that because of conservation of mass. And then this is also a laminar flow, right? Which means that like the amount of water at each cross section is actually the same. Okay, so because V1A1 is equal to V2A2, but then, you know, this is A2 and this is A1. But we also observe that A2 is less than A1, right? Then what does that imply about the velocities? Actually, no, that's not. Okay.
Well,
this
no, V1 would be
is the
less than
wrong
V2.
order. This is the wrong order, sorry. Okay, so first of all, what do we know about the velocities of the two things at the different places? V2 is greater than V1. Good, because it has gone through the influence of gravity for a longer time and has accelerated, therefore V2 is greater than V1, right? And then therefore, what does that imply about the areas? Yeah, then that means A1 is greater than A2.
Now, this is why water stretches out into like a very thin stream.
Yeah.
But of course, there's a limit. And what happens at that limit? Like if we stretch further and further down, what is eventually going to happen? Because it can't just keep decreasing forever. So what's going to happen at some point? Turbulence. That's a little bit different. That's turbulent flow. It turns into a solid spark of ice. No. Have you guys noticed that like if you go far enough down a faucet, it'll start dripping droplets of water instead of a stream? Well, that's because it's going to get so small that eventually the surface tension of the water will just become too great for it to be broken and turn to keep it in a stream. So it's just going to collapse into a little ball. And that's why it drops little droplets at some point. Yeah.
Yeah.
Because it can't just decrease forever.
So at the end, it's gonna go into like a stream that's so small that's just gonna start like dropping. This is why rain doesn't fall in streams. Rain doesn't fall in streams. Oh yeah. I'm actually not sure.
Well, rain doesn't fall in streams because they form as individual droplets. So that's a little bit different.
That's a different thing. Okay, and the second Bernoulli principle is there's a conservation law with fluids actually. Conservation law of fluids, which is that if you take like half times the density times v squared plus rho gh plus p, which is the pressure, right? This is actually going to stay constant throughout the entire liquid. All right, and this is so this is true of like any liquid particle in a body of water, that like this quantity stays oh, my bad. I should stop writing the p's as lowercase. All right, there you go. So the rows are the lowercase looking ones and the p is the uppercase looking one. All right. Yeah, so in a body of water. Now this might seem like a weird combination, but it's actually like a really useful thing. So to prove that, we want to take a look at like water flowing through a pipe, right? Conservation, yeah, it uses conservation. Yeah, no, it uses work energy theorem. Okay. And we're actually going to use the, we're going to use like the last thing that we derived. Oh yeah, this is regarding like water flowing through a pipe. Yeah, the momentum, no, this isn't the momentum. This is half rho v squared. That's the, that's like, that's not momentum. But rho gh is like the pressure, and like P is the other pressure. Okay. So let's consider like a particle of what is 1/2 rho. It's not like a specific quantity, but we'll get it. This is like the fluid kinetic energy, if you will. It's kind of like a weird thing, but That's all right. So if we think about like, ooh, this actually isn't pressure. This is, All right, I'll just call it P.
Well, it was just K over V, but we usually just write it out 1/2 rho V squared.
Yeah. So let's consider like a water particle that flows through a pipe, right? And then this is the water particle at 2 points in time, right? So at this point, it has pressure of P1. It travels some, delta X, right? And then it arrives at the second point, which has a pressure of P2, right? Okay. So now from the work energy theorem, right, we know that the work done by external forces is equal to the difference in energy of this particle, right?
That's a W. Oh, P with underscore?
Oh, that's not an underscore. That's just capital P to differentiate it from the lowercase p. Right, so then in that case, we have to calculate like the delta E, right? So what is delta E? Delta E should be equal to the difference in kinetic energy, right? Plus something else. This is equal to, well, if the thing has like a mass of dm, then this is equal to like plus dm times rho times h, and then delta of that. So like, wait, did I just say delta d? No, delta m. Delta of, okay, no, it's delta of dm rho h, right? Okay, so what is this quantity here? Yeah, it's like it's the potential energy, right? Because, so what is m rho h? M rho h is equal to like the buoyancy force times the density of the object, right? Yeah, so then is it that? Oh god.
Um,
Kind of awkward.
well, or are we talking about delta dm rho h?
Yeah, so
Well,
this is like fluid potential energy, basically, because like if you remember in like gravity, right, the UG is equal to mgh. This is similar. So U of the potential energy of a fluid is equal to like m times rho h instead of g. Yeah, and this is like only for like a flowing particle, because if you have like water flow, then it has more potential energy here than here, because like the flow of the water is going to carry the particle from one end of the tube to another, right? Therefore, there's going to be some, change in fluid potential energy. Anyways.
you put a G
Oh,
there.
yeah, it's m rho h. So there's like a direct correlation here. Anyways. Okay, so we know that the work external is equal to the change in energy, right? So then delta K is going to be equal to half times dm times delta of v squared from point 1 to point 2, right? So now we can, now we can apply the work energy theorem, right? We get dw is equal to delta E, which is the difference in kinetic energy, right? Which is half dm of, well, first of all, let's define this as like force over a distance, right? So then since it travels delta H, then it is, or since it travels a distance of like dx, then we can say that it is some like force, right? F1 minus F2 times dx, right? So it's force times some distance. But then what this turns into is because the force is equal to, like the pressure times the area, then we have like P1 times dA1, which is like whatever area this is, P1 times dA1 minus P2 dA2 dx. Shouldn't F1 and F2 be the same because gravity is constant? Well, no, not exactly. Because the force is by the liquid, not just by gravity, right? So the force is caused by pressure on the liquid. So it shouldn't be the same because, yeah. Anyways. And then FTV. Is there a dV here? Andrew, is there a dV here?
A dV?
Yeah.
Well, let's check the units. So this is F1 minus F2 is newtons, dx is meters, so Newton meters. I don't think there should be.
Actually, no. What we actually want is what is going on? It's just me confusing myself a lot because I'm tired. I'm sorry. I'm sorry. Today has been a bit like. Turbulent because I can't
Nice
actually.
pun. By the way, turbulent flow is way cooler than laminar flow, but it's also way more complicated, so we will not be covering it. And also the F equals ma doesn't cover it. Just letting you know.
Yeah. I didn't actually write the derivation clearly enough to understand it at this point. I don't know.
You want to save this for the notes?
Right, work external equals to delta E, which means that, all right, let me redo this. So delta E would be equal to like delta K plus delta U, right? But then the work external is also equal to the difference in pressures, right, times the distance. So would it just be equal to the difference in pressures? Yeah, it would be.
Yes.
Don't you also need area? No, because area makes it into a force, right? But then I want to describe like work. So because pressure is different between the two areas, then we have like the work done between them is equal to the difference in pressures. Yeah, okay. Okay, now I think I have something. So P1 minus P2. Yeah, work equals to force times distance. But then like the work is equal to dx times F1 minus F2, and this is equal to the change in area times pressure, right? So this is equal to dx times P1 times area 1 minus P2 times area 2. All right, yeah. All right, Andrew, I need a little bit of help here. I'm sorry.
Okay, so let's go back.
Oh my God.
So let's see what's going
My
on.
brain is absolutely fried. I'm so sorry.
It's okay. I've just emerged from college application season, so I'm probably no better. Let's figure this out. So where are we right now? We want this fluid work, right? So it's F1 minus F2, okay, times dx. All right, let's see where you're at. Oops. I think this is where is this going to be on the exam?
Well, you need this conservation law on the exam, but I just like, I am currently forgetting how to derive it because
Okay, I think maybe it's best to
brain
distribute
doesn't
here.
right now.
I think you distribute here. You get dx p1 a1 minus dx p2 a2.
Yeah, and then ADX is equal to volume, right?
Yes.
Okay, we can continue this.
So then you have the volume flow rate.
All right, we can continue this. So this becomes like P1 times V P1 V1 minus P2 times A2, right? But then because of volume flow rate, then this is constant. Oh, I wrote A again. I really, right, but then this can be like the differential in area. So yeah, we're assuming it travels a very short distance, so then we can use like differentials here. So P1 dV minus P2 dV is equal to the difference, the infinitesimal difference in work. Right, so then we can factor out a dV here to get dV times P1 minus P2. Right, but then now we have like a D on both sides, so we can kind of like divide to make this a derivative. It's like that physics thing that math doesn't agree with.
Just divide by the
Yes,
divide by the
divide
particle.
by dV. We get dW dV. Wait, okay, so
Okay, so just
let's rephrase this.
aren't the volumes different
Okay, but the flow rates are the same.
by the continuity equation?
Yeah, so so this is V1 and V2, right? But then here, we proved that V times A is always going to be the same in a tunnel, right? V times A is always going to be the same in a tunnel. But we also get that.
By the way, this is why squeezing a juice box will not only get the last bit of juice out, it'll also make it squirt out faster because you're making the area smaller.
Do you think it's more safe to continue this tomorrow, next week?
I think it's safest to relegate this to the notes and cover some of it during office hours if you're feeling up to it.
We don't have that much of the derivation left. We can just do the next week. All right, yeah,
Okay.
we're sorry. Yeah, I'm like currently forgetting the derivation of this, but
Alvin, go splash yourself with water. Your brain is dying.
yes, I need to splash myself with water. Yeah, like there's not that much of this derivation left, and then we'll give like a problem and then move on to the next thing in the next lecture.
What matters is you understand that it is true. Like that is by far the most important.
Like the important takeaway, bar the explanation, is what's in the red box here, which is like your kinetic energy plus your potential plus your pressure is constant. And then that's like used in a lot of places, but yeah, I'm forgetting the derivation right now. I'll have it next week though. Or if you want to come to office hours, you can hear it there too.
Yeah, I think next week we should talk a little bit more about relative. Did we do relative motion?
We did.
Okay, so then dimensional analysis. We should cover that during either office hours or next week.
So I'm gonna end it a bit early today, because
Yeah.
Lord. Yeah. So next week, one more F equals MA. Come to us for any problems that you might have trouble with. We'll be doing office hours, for which you can do that, or
I
yeah,
don't think tiers are a
there are a
laminar
couple
flow.
problems next meet as well.
Tiers are a laminar flow.
Yeah, next meet we can also go over like start doing problem solving strategies like dimensional analysis.
Yeah, so we're kind of getting into the home stretch here. So let's see. The F equals MA is in just a little bit over a month. So at this point, practice on your own, review the notes. Excuse me. I'm going to be like making some adjustments to the notes to make them a bit more complete. But really, yeah, just go over the practice problems again, go through the practice sets, look at the notes, and do some practice F equals MAs. We're kind of basically wrapping up theory at this point.
Okay, guys, ignore everything that happened on this slide, okay? It's like, in principle, today ended here with the laminar flow thing.
This painful last.
I will do this with a clearer mind on, or I will do this again next Tuesday. So yeah, just watch out for the F equals MA on the Google Classroom, and yeah. So if no one has any questions, y'all are free to go.
Adios, guys. See you guys at office hours or next week.
All right, bye. Dear Lord.